All right, welcome to this session. We want to look at some bit of some chemistry, and with that, in the context of chemistry, we want to look at how we can find the Kc and the Kp values and how we can express them in terms of their concentrations, and also how we can express them in terms of their partial pressure equilibriums. So basically, we're looking at chemical equilibrium, and after that, we want to see how we can work out such kind of questions. Question 1 is saying write equilibrium constant expressions for Kc and Kp for the following reactions. We've been given the first reaction, the second one, the third one, the fourth one, the fifth one, and the last question there. So for today, I want to focus much on how we are supposed to express the equilibrium constant expressions for Kc and Kp for the following reactions. So before we start, let me first of all explain a few things. So, as I said earlier on, we are looking at it from the context of chemical reactions. So, we are looking at it from the context of chemical reactions, and the key word that we want to focus on here is the word equilibrium. What do we mean? Let's take, for instance, we've been given a chemical reaction. We've been given a chemical reaction, and we know to say the constraint of a chemical reaction is we have got reactants, and in that chemical reaction we've got the products. And you know to say it is the reactants that form the products. In the absence of the reactants, we can't have the products. And let's take for instance to say amongst the reactants, let's represent them with A, and the product, let's present them with B. And in an equilibrium reaction, it means that the rate of the forward reaction is equal to the rate of the backward reaction, or is equal to the rate of the reverse reaction. We know to say for this B to form, or the products to form, we need the reactants. And equally, we need the products for the reactants to form. So when the rate of reaction between A and B are the same, it means that this reaction is in equilibrium. To mean that the rate of forward reaction is equal to the rate of the backward reaction, or is equal to the rate of the reverse reaction. So when the two reactions are balanced and the concentrations in between A and B are not changing, it means that this chemical reaction is in the state of equilibrium. And what kind of equilibrium are we talking about here? Let me give the best example to illustrate what I'm talking about. You've been given a village, and this is village A, and the other village is village B. And then village A has got 1000 vehicles, and village A has got 1000 vehicles, village B has got 1000 vehicles. And then you've been told to say the vehicles that are moving from the village A going to village B are 10 vehicles, and the vehicles that are moving from village B going to A are 10 vehicles. You've seen that. So it means that village A is losing 10 vehicles. So meanwhile, as it is losing these 10 vehicles, you are equally getting the amount of what it's losing. So losing 10 vehicles and getting 10 vehicles. So you discovered to say there is motion between village A and village B in terms of the movement of these vehicles, but the concentration or the number of vehicles in A still remain the same. They won't change because the more we lose the 10, we are getting it from village B. So this is the point I'm trying to emphasize here. The concentration between A and B are the same. Nothing is changing there, but the rate of reaction is taking place, and this kind of equilibrium is called dynamic equilibrium. We call it dynamic equilibrium. So in dynamic equilibrium, you are able to see that the rate of the chemical reaction is taking place, but the concentrations of A and B are the same. They are not changing. So this is what we mean by dynamic equilibrium. So you now can explain to somebody out there what it means when they say this chemical reaction is at equilibrium. It means that the rate of reaction, the rate of the forward reaction is equal to the rate of the backward reaction, or is equal to the rate of the reverse reaction. This is what we mean by chemical equilibrium. So in expressing chemical equilibrium, we can use different type of methods, and if you look at the question that we've been given here, we've been taught to say we need to write the equilibrium constant expressions for Kc and Kp for the following reactions. So for Kc, we want to look at the question here. Let's express it in terms of Kc. So a Kc, we're expressing this chemical reaction in terms of its concentrations. So, and the formula is very easy. You just look at it from this angle. We say Kc is equal to, that's not Ke, that's Kc. So you just say Kc is equal to the product divide the what? The concentrations of the reactant. And you note to say your product here, you've got carbon dioxide, so we're expressing it in terms of concentration. That's why we're saying Kc. So either Kc is used or K, they equally mean the same thing, but there's a fine distinction between Kp and Kc. Kp, we're expressing the reaction in terms of its partial pressure equilibrium, and in such cases we usually get to use and deal with the gases. So remember that there's a fine distinction between Kc and Kp. Kc, we're expressing the entire chemical reaction in terms of its concentration, but for Kp, we're expressing the entire chemical reaction in terms of its partial pressure equilibrium. So what we have on the side of the product, we've got the concentration of carbon dioxide, there we go, and we've got the concentration of hydrogen, and then you divide the reactants. On the side of the reactants, you've got the concentration of carbon monoxide, and you've got the concentration of water. So this is how you write it, and then you are done from this, and that's how it works. So for Kc, uh, this is what it means, that you've got the product, then you divide the reactants, and then you work it out